Hello to all of our attendees, for those attending in person today and those joining us on Zoom. Today it's my pleasure to introduce Professor Jeffery Roesler. Professor Roesler holds the Ernest J. Barenberg Professorship in the Department of Civil and Environmental Engineering here at the University of Illinois Urbana-Champaign. He has conducted research on concrete materials and pavement systems for 25 years, and he's recently working with a focus on 3D concrete printing, layer compacted concrete pavements, fiber reinforced concrete, microscale urban heat islands, and non-contact ultrasonic sensing of concrete. He's also a registered professional engineer in California and the past president of the International Society of Concrete Pavements. I would like now to invite Professor Alcadi to come here and give some words for Professor Roesler. So please join me in giving a warm welcome to Professor Alcadi and Professor Roesler.
Professor Roesler, he's worried that I'm going to say bad things about him when I'm going to do the introduction, but I will disappoint him today. I think it's always a pleasure to have one of your colleagues presenting. Professor Roesler is a pioneer in his field. If Lev is watching this, I will say he's one out of two that I think that they are best on pavements. If Lev is not on the Zoom, then we'll pass on that about that. He has been doing an amazing job in developing new technologies in the concrete pavements, in the airports, as well as in the highway. And recently he has been working as part of the team that we have on the CCAT that he's going to be discussing in some of the innovative work that it's going to be for the future of the connected and autonomous vehicle. So away from all this, he's a very close friend, and I'm always honored that we keep bouncing all the good ideas together. So I don't want to go long on this. I just want you to hear what he has to say about this innovative work. So please join me in welcoming Jeff Roesler.
Thank you for the kind words, introduction, and Ahmad. And excited to present on this topic. Because there's a few seats in the front if you want to sit in the front. Well, the topic here on vehicle to infrastructure, pavement-coded signage for a construction work zone does not seem like a topic I should be presenting on, right? Seems like a different field, or somehow I stumbled into this, and part of that's true, actually. And one of the opportunities in being involved in centers like the one that I'm involved in with a team of faculty is that you can work on problems that are kind of at the boundaries of what you typically work on, and hopefully with some new thinking and some good students, you can make a contribution. So there we go. Did I do something? Okay, so I'd like to thank the Center for Connected and Automated Vehicles or Transportation at University of Michigan. That's the center, CCAT, as well as Illinois Center for Transportation, which houses the part that the University of Illinois is doing. This work can be found in several publications that are on the ICT publication page. These are reports. We do have a paper out on some of the things you'll see in this from a PDEG. So a PDEG, Sakunea here, he's the PhD student working on this. And we've also filed a few patents on this idea that, well, the patents don't mean anything except you can get protected. Doesn't mean you're making any money. Doesn't mean anybody's actually even using it. But anyway, we're hoping someone uses it. So a little bit about the problem, why we're doing it, then a little bit about some work previously, because it connects to what we're doing. And some of you may know about it, and it kind of helps fit into why we're doing this on construction work zones. And then really getting into some of the details of what we've developed for construction work zones. So the motivation, and I think this has kind of shifted over my career, really in the transportation sector, even the work that most of you do here has a component of safety. 40,000 deaths a year in the US on roadways. And I was reading yesterday that they're expecting a 4% decline. So that may put us under 40,000, but that's still a lot. FHW has a vision 0, which means we want to move towards 0 traffic deaths. That's a high bar. We're not getting there very fast. And I would propose that some of the stuff in the vehicle technology space could help us get there a lot faster if we have a bunch of people working on it, thinking about how to really improve safety. Another interesting fact, lane departures lead to about half of the fatalities. Doesn't mean, I mean, lane departure could be because you're distracted and texting, but the point is lane departures. And just one thing I want to point out is, although I'm big on connected and autonomous vehicles, but the broader topic of vehicle technologies, advanced driver assist, are kind of really important because they're here already. And how can we use those? Kind of connected and autonomous vehicles are kind of a subset of advanced driver assist systems. And whatever we do, because we're engineers, is that we have a lot of roadway miles, whether it's the US or anywhere else, to apply this to. So we can't think of just a single case that we can use in brand tool, and it has to apply everywhere. And that's kind of a big challenge. So we have all these sensors on the vehicles that can do amazing things. They can tell us can automatically stop our vehicle from collisions. They can keep us between the lane lines in many cases. And they can do adaptive cruise control. So how do we use this better where we use the roadway as a sensor? And so that's the challenge, because most of you work on transportation in terms of the pavement and material side. And so keep thinking about how do you use the roadway as a sensor. What are the big problems? And some of you've seen this. If you've driven in vehicles with lane assist in adverse weather, they don't work so well. They can't detect the lines. That's how they work based on computer vision. That's kind of how we got involved in this, is the lane assist systems don't work that well. They work well in Phoenix where it doesn't rain and you get always sunshine, or the Bay Area where you don't have any rain most of the year. So how do we do this better with what we have here in the Midwest? And one of the former PhD students came up with this idea, is if we change the electromagnetic signature of roadway materials and we kind of focus an area where we can detect a high electromagnetic flux, we can detect it, we can keep the vehicle in the road, but without any contact, and also without any active sensors. These would just be passive sensors because it's just bending the Earth's magnetic field and we're detecting it. So this was Sachendra Dahal's PhD thesis, and it could work very nicely and complement what current vehicle computer vision works. And so you're just creating a material passive sensor that goes in the host binders that we already use, whether it's cement or asphalt. And how does that work? Well, we imagine a sliver of the roadway has this material, electromagnetic material. You could just put some ferromagnetic material like steel, and you have these little magnetometers, which this is about the size of them. They're not that big. These magnetometers can detect changes in the electromagnetic field of the Earth or the area, not just the Earth. And you can put them on a sensor body, and then you can then detect when you cross over this area with various sensors. So it's pretty simple, actually. And this seems, the nice thing is you can use a lot of different types of materials. You can use steel. There's other types of ferromagnetic materials that are high magnetic permeability that are easier to detect. But the point is, it's not just a one material that you can use a lot of different materials to do this. And we showed that successfully. This is an example of a signature you would get from these electromagnetic materials. If you put them in a small sliver in the roadway, this is the center of the roadway, you can see that you have a very large detection. These magnetometers detect nanotesla, and we can detect we feel like we can detect 300 nanotesla, then we can consistently process the signal. Here you have almost 2,000 nanotesla, so this is very easy to detect. But these are very small changes, and we can do it pretty easily with very small percentages of materials in the roadway. We later put these sensors on a vehicle that happens to be Sachendra's car. Thankfully, he had a car. We bolted those on and we ran these tests back in the back here where we looked at different weather conditions and whether we could detect where we are on the roadway. And worked very nicely. In fact, camera-based systems, you know, in good weather, you know, they can detect, you know, where they're supposed to be within 1 or 2 inches. And when it snows, which is the other shades here, they have much higher air because the snow causes the camera system not to work so well. But with the electromagnetic materials and the magnetometer, we can still be under 2-inch detection because we're just detecting magnetic fields. So this was Sachindra's work. And so imagine now that we're trying to use the new vehicle technologies to control the vehicle where it's in the position of the road. And if we can warn the driver they're going off the road, not even drive the vehicle autonomously, then we should help with this Vision Zero goal. So we need to modify some of the roadway material with, you know, some amount, and we need to do it efficiently. And if we can also do this in many different weather conditions, and so we're not kind of confined to nice weather to drive autonomously in the future. We can do it anywhere. Okay, so that's kind of my background. This helps you see what we're doing now. So we got into work zones, and so you may ask, why did we pivot into construction work zones? So we finished Sachindra's work. We applied for a patent for that. We actually started a business because we had to get more funding. But we decided we had to pivot. So anybody have an idea why we had to pivot?
Maybe because construction work zones offer you more flexibility to implement the passive sensors you need to install.
Okay, so that has part to be the answer. So we actually went and talked to a bunch of people who own roads, safety engineers, and we found that most people didn't have a great understanding of how the vehicle technologies even worked. So the problem we were looking at actually was not even something they were thinking about or worried about. So we were, I wouldn't want to say we're ahead of what's going on, but the idea that your customer, the people who own the roads don't even perceive this to be a problem, but they did perceive construction work zones to be a problem. They knew about people that had gotten in accidents or hurt or killed. So they said, well, but if you could use this in construction work zones. Now, it wasn't necessarily something I wanted to do, but that's what people said they would be more interested in. So that's why we pivoted, not because we really wanted to, but that's just the reality. So we decided to look at, okay, could we use this and tell vehicles maybe some more information that they're currently getting when they enter construction work zones? And that's when a PDIG kind of showed up on the scene. So luckily we had a student who was here and we had a new problem to look at. Now, interestingly, I said we had around 40,000 deaths. Construction work zones, it kind of peaked out close to 1,000 fatalities. So not the biggest problem, right? 40,000 versus 1,000, they're all bad deaths, but this was the one most agencies thought this would be what they would be more excited about doing. So we wanted to tackle, okay, what's going on in construction work zones? And a lot of research is going on in construction work zones. And luckily there's some funded projects here from ICT on construction work zones. I think Professor Oyang was involved. I found out he was involved. We read his report with Professor Khalid El-Reis and found some very interesting data in there that we could use. But really in construction work zones, you have generally there are higher propensity to happen in high functional classes like principal arterials or interstates. You have more accidents where overall in construction work zone due to distractions. And then finally, in the last one, you have more likelihood of commercial vehicles being in accidents in construction work zones than in the general roadway, okay? So there's different reasons for construction work zone safety hazards relative to normal roadways. And so we kind of, this was in there, this is actually in this report by Khalid El-Rais and some of the other faculty members. But unsafe speed conditions were a primary factor that kind of fits into the previous slide. People then, because of the speed, they were changing lanes. And of course, you have a work zone where lanes get, you lose lanes. And then finally, where were the crashes? Well, they were typically before the work zones where people were speeding. And then people have tried a lot of countermeasures, but we found one that was interesting that was in this report on in-vehicle messaging that seemed to show some success. And if we warned people in their vehicle, not just a visual that they can see, but actually an audio visual in the vehicle that it may be safer. And so this is a study done in 2018 that was published, and it showed that if, for instance, this green line here was, there was no message to a vehicle entering, by the way, this is simulation, not real. If no message before a construction work zone started, this is at 0, this would be the average speed of the simulated driver. If you did give some mixed messages, that's audio and visual, you can see the speeds decrease quickly and they decrease all the way to the construction work zone where it started. The other interesting part was that people tended to merge quicker when they had a mixed message in the vehicle. So we started thinking, well, if we can give the vehicle a message early inside the driver, and we knew this, that your new vehicles have an easy way to give audio visual messaging, right? You have a screen, you have speakers, then that's very possible. So this is where we came up with something pretty simple. I don't want to say it's very complicated, and this is what we applied the patent for, is if you could just imagine making patterns in the roadway. We called it now we call it invisible markings. You can make patterns like four lines like that. We can detect speed. If we have diagonal lines, we can tell the vehicle to move over. So we have patterns we put in the roadway, kind of like a QR code, not exactly though. UPC symbol probably is more accurate. But then the vehicle reads these patterns and says, this is what I'm triggering to tell the driver. We could also have another pattern say you're leaving the work zone so you can speed up, things like that. So we basically, the short summary is if we put these patterns on the roads, then we can detect them with the vehicle in theory, and the vehicle has to process the signal quick enough and tell the driver what to do. So that's the idea. So the first one we came up with is, it's pretty simple. The algorithm is you just have equally spaced transverse lane markings, or invisible markings, are really not lane markings. This would be your electromagnetic material. And if you detect them, if the time to cross them for the vehicle is less than the speed limit time, then you just tell the vehicle that they need to slow down, or if it's the merge, this is our merge left. So we trigger this, and if you sum up the times at different sensors, you can then, the vehicle recognizes they need to merge left because it sees that there's a diagonal pattern on the roadway. So this is the idea. We thought it could be pretty, we didn't think there was nothing, it seemed like no one was actually looking at this. I mean, people have been looking at messaging boards and rumble strips, and there's nothing necessarily wrong with those, but we wanted to have something where the data suggests this is much better, particularly with the distracted drivers. So the first step was to build something in the lab, and we just quickly bought some magnetic tape that we could put on top of some strips. We had a kind of a robotic frame here that this could move like your car could move, just at very low speeds, but just to make sure that we had understood how this would work and how we would process the signal. We had our magnetometer sensors here set up as such. By the way, we have to set up 2 magnetometer sensors because this detects the Earth's magnetic field. So does this one, but this also detects the magnetic particles here on the tape. And when you subtract the two, you just focus on the magnetic particles. So these magnetometers actually pick up the Earth's magnetic field. So if you don't subtract them out, then you actually have no way of resolving the signal. I'll show a picture of that later. This was done though, where we have our sensors here. We just had some strips, and we wanted to look at different spacings and different orientations. We did a lot of different pilot studies on this just to understand the system, the acquisition rates, what the signals look like. And initially we realized that when we did like 1 foot spacings, which we didn't think we would do in the field, but in the lab, we ended up getting crosstalk between the different magnetic lines because they're too close. The magnetic fields kind of overlap, and the sensor had a hard time picking them up. So when we moved the sensor strips, or excuse me, the strips further apart, you can see that the sensors clearly detected each of the lines. Here I'm just showing, these are 4 different sensors on the sensor bar that you can see. So we're just looking at the peaks, which means the sensor is basically over. And if you get the times that the sensor crosses, you can then calculate the speed. Obviously, this was a slow moving robotic frame here. So 0.14 meters per second, that's really slow. We wouldn't expect that outside, obviously. And this is what our sensors look like when we did them incline 60 degrees. So you can see the offset now between sensors that are over here versus sensors that cross over here. So you see all these delay times. So when we speed up, obviously the delay times are going to be less, but you can still pick them up as long as you have your data acquisition rates are higher. That's an example where you could create a pattern where you recognize it, let's say an exit right or something. That was just another idea we had. Okay, so that was done late 2023. 2024, we focused on a few things. One note is we had these sensors were called one-axis magnetometers, and they just measured the electromagnetic flux kind of in the vertical direction, like in this direction. But actually, magnetic fields have 3 directions. So we wanted to test a new sensor, so a 3-axis magnetometer, to give us more redundant information, because sometimes the sensors have noise on them and you can't resolve the signals. So it's good to have multiple axes reading the same type of signal, or at least similar signals. So that was one of our new things. We also wanted to expand on a question that people always ask us, well, what if I don't want that electromagnetic signal in the roadway? How do I get it out? So before we talked about embedding electromagnetic particles in the road. Well, how about if you want to turn that off? Can you do that? Or do you have to rip out the road, particularly in construction zones? Because construction zones will be temporary. So if we imagine embedding the ferromagnetic material in the roadway, we can't take it out very easily without obviously taking up the asphalt or the concrete. So I want to show something about that. And then we did a few field tests that you'll see in a second. Field test means outdoors for us, not necessarily with the vehicle. We're doing a vehicle test now with Professor Talipur. So let's talk about the programmable signatures. So we started this back in Sachindra's thesis, but essentially, if you can imagine, would it be possible to have a signature that we could program to be turned on and turned off? Wouldn't that be nice? So if I wanted to have my lane keeping feature on during the construction and then I wanted to turn it off, could I do that? And it turns out there are materials that you can do this with where you can magnetize them at fairly low temperatures. And so that's what this Curie temperature means. So there's certain metal oxides that I wasn't aware of, but the student found this out. So students, keep bringing good ideas to your advisors. And anyway, at 120 Celsius, if I heat this material, it turned out to be chromium dioxide, which is that black powder there. If you heat it to 120 degrees, and then you apply a magnet to it, it becomes a permanent magnet as long as you let it cool down with that permanent magnet. And if I want to turn it off, I just heat it back up to 120 degrees Celsius. We picked 120 because we didn't want to have anybody with asphalt get upset. So we figured if we could keep below the flash point of asphalt, then we could magnetize and demagnetize this. So this is the idea of a programmable signature where we could turn it on and off as we wanted to. And this is just a little figure to show that if you have like chromium dioxide that is demagnetized, if we heat it above 120 degrees Celsius, we can align its dipole moment such that I can make it very magnetized. And as soon as I want to demagnetize, I just turn it to 120 degrees without the magnet and it goes away. That was a nice little feature that the student figured out. So we did some lab tests where we put some chromium dioxide in the top of a fresh concrete. So we just embedded it in the top 5 millimeters of a concrete prism. We then heated the whole thing up in the oven to 120 degrees Celsius. Then we applied a magnet, and this is a magnetic, these are some permanent magnets in a frame so that we could permanently magnetize that specimen I just showed you. So you have these permanent magnets that magnetize the chromium dioxide. So you can imagine if I put this in the roadway, I could have a truck that drives over it with these permanent magnets and a heater to create a magnetic field in this material. And this was our little test here where you have the chromium dioxide being magnetized. And because the magnetic field will mimic what the permanent magnet has for features, you have to be careful how you orient the material. So we're trying to maximize the vertical orientation of the magnet. And then we did another test where we turned it 90 degrees to see how the magnetic field, we could change it to have a different signature. So those were two cases. So this just gives an idea of, this would be the unmagnetized material. It's not always zero, but it's pretty close to zero. This is the signal. And then if we magnetize it, you can see it's about 8,000 Tesla, pretty high. We only need to measure 300, so this is probably too much material, but this was just our first. Then if we heat it again, we just demagnetize it. Same specimen, we just heat it above 120 in the oven, take it out, and it demagnetizes it. And then we tried the second pattern, which was on its side. And when you magnetize that same material with a different orientation of the magnet, you can see you get a different signature pulse. So you can actually embed not only you can embed signatures that you could detect, you could tell some more information about what you want to do in that magnetic field. Okay, so a PDEG then took this information that we had been working on and decided to build some invisible markings so that we could do construction work zones a little more efficiently. And he built this cart here that you see. This cart is the schematic of this cart here. The magnetometers are these things at the end of the PVC. And these are 3-axis magnetometers. And essentially we built some concrete with some epoxy that we embedded the chromium dioxide on. We had a heating lamp here. And then we also had some permanent magnets that it's hard to see, but they're over here, that can magnetize this material. Then we're going to put these markings outside so we can actually do some measurements. So this was an initial study. A PDEG reminded me this was in his apartment parking lot. So this was field study number 1, I guess. And for this study, we had a cart and we were basically looking at what percentage of this material we needed in the epoxy paint markings, essentially, to be able to detect this pretty repeatedly. And this was like the magnetic tape here. This is 10%, this is 20%. This is the vertical detection of the magnetic field. So as the cart goes across the magnetic or the invisible markings, there's a magnetic field that we detect vertically, and that's these peaks. There's also a magnetic field in the Z direction, which is the forward-looking direction. So the magnetic field that the lines kind of move in the forward-looking horizontal direction, that's some of these lines, and those aren't so great, although you can see them here. But there's a lot of noise. And there's also a Y direction that I didn't show here. But at least we decided that 20% was probably a pretty good number based on knowing what signal we could look at, our signal processing. Somewhere between 200 and 300 nanotesla was what we could detect. So we decided to make most of our specimens with 20% of the chromium dioxide for this particular study. It doesn't have to be this type of material. There's other materials that can do this. And so we then built some more samples. And this was parking lot number 2 by Uni High. We didn't even have to rent it because no cars were there in the summer. At least that's, I mean, we had some good runs here. So we wanted to look at the magnetometers again, look at our invisible markings. And then really this time we wanted to focus on a little higher speeds, which means he had to run really fast in the parking lot. And we wanted to make sure our signal processing would work correctly. So these are the invisible markings, even though they're on a kind of fiber cement board. If you can imagine this in the outside, we would probably just kind of spray a epoxy material that's clear, and it would just look invisible. You wouldn't have to see it. You wouldn't want it to be seen actually, because it would confuse drivers. So we have our magnetometers again here. We have 2 rows of magnetometers because you need both rows to cancel out the Earth's magnetic field, and power supply, of course, and then data collection system. So this is our first test where we had 8 strips in a row where we tried to measure a petage's sprinting speed. So we'll see how fast he can run. It gets up to 15 kilometers an hour. So that's pretty good. I don't know, is that as fast as you could go? So these again, this is another picture of the invisible markings. These are the magnetometers, the 3-axis magnetometers, so very small. So what's the data look like? So this is the data that comes out of the magnetometers. 2, 3, 4, and 5 sensors are sensing the vertical direction here. But note the units here. This is actually in nanotesla. So this is like almost 50,000 nanotesla. And the reason why this looks kind of strange is because we only showed you the bottom sensor rows, and this picks up the Earth's magnetic field as well. So you have to subtract the top sensor from the bottom sensor, and that subtracts out the Earth's magnetic field, which is around basically 48,000 nanotesla. So the Earth's magnetic field is way higher than the magnetic field we're altering with these materials. And it works out very nicely when you subtract them. And then you can also zero each of these measurements because they're kind of, we make this relative to the start position. So once I subtract out Earth's magnetic field, I zero the signals. Now it looks like something reasonable that I can detect. You can see there's still noise in the signal, but these are all the same material in the X direction. And if a petage, he's not going to go exactly straight. So that's why you see difference in the peaks. Could be something to do with the materials not being mixed uniformly either. But so we had to do a little bit more signal processing. And so we did some more processing where we basically took the change in the electromagnetic flux after each data point. So we just took the difference between consecutive points. So it's kind of like a derivative. It's not exactly. And we get this. So this even looks better. So this is the change in a magnetic flux here on the x-axis versus time. So we can then process the first peak here very easily and calculate the time. The times between the peaks would tell us my speed. And we could do that in approaching the construction work zone or in the construction work zone, and then tell the vehicle, this is how fast you're going or slow down. This would be after filtering the data. So we also did a high and low pass filter. So this is one more filtering step that we wanted to have so we could see clear signals. So this is 4 different sensors. So that's what the different colors are. And note again, anywhere between 2 and 300 nanotesla, we can detect pretty accurately all the time. So this looks pretty promising. And if we then take the peaks of those, this is looking in the Y direction now. So I'm running on the cart and I was looking at the magnetic field in the vertical direction. I can also look at it transverse to my direction. And you still get some pretty good signals that we could calculate speed on, but it misses some of the markings. And that's because of the way the magnetic field's been created, that we miss some of the horizontal transverse components, depending on how we move the cart. And we also did it for the Z direction, which is the forward-looking direction, and we got most of the peaks with the Z direction. So we would just calculate speed then based on the peaks, like these 4 sensors versus those 4 sensors, and the next invisible marking and that time difference and the spacing we knew it to be 10 feet, then we can get the speed. And we could also do it for the Z direction. That was for the X direction. X direction was up and down. I know that doesn't make sense. Z is forward. We can do the same thing. And then this is a recent paper we published. So these are the back calculated speeds from those signals. For all 8 of the sensors, you can see that anywhere from 12 to 15 kilometers per hour. This is what the GPS speed was that you saw on the camera. So it's pretty consistent with what that was measuring. And we could do that with X sensors or the Z sensor on that magnetometer. So the multi-axis magnetometers were nice because we could verify speeds with different directions of the magnetic field. Finally, I won't spend too much time on this. We looked again at particularly the inclined lines that would tell cars to merge, since that's a major issue. We could also find speed with those inclined lines. You can see the inclined lines. So even though these are inclined, I can still find the speed, as well as looking at different sensors transversely, I can tell the time differences, and then I know that it's an inclined sensor or marking. And we do the same thing. These would be the speed sensors only, and then these are the inclined sensors. You can see slight time differences between the sensors because they're offset transversely. This would be speed. These are all the same. When they're all the same, that means the sensor's transverse, or the marking's transverse. And then these are showing, again, different time offsets. So I can calculate speed, and I can tell if it's merged left or merged right. And these are the key points for the merge here, that the time differences tell us that I have a merge. So it's not that different. 2.76 seconds versus 2.84. That's down in the 100 seconds, but you can accurately pick that up with your data acquisition system. Okay. So hopefully I went through a lot of slides there, a lot of experiments, but I think hopefully I've argued that construction work zones need some improvements. So do lane departures, for that matter. And I think advanced vehicle systems can get us there, can be part of the solution, not the only part of the solution. So this idea of using the road somehow as a sensor, I think there's a lot more work to be done in this area. Magnetometers, we need those on the vehicles if any of this is going to work. And they're very inexpensive sensors. I think if you buy them in bulk, we can get the cost. These are not like LiDAR. LiDARs cost you, $5,000, $10,000. These sensors should be around $100 in bulk, probably even less. We can use programmable materials where we can turn them on and off. And I showed you chromium dioxide was one example. And by putting these patterns on the roadway and they're kind of invisible, we could, tell the vehicle different signals pretty easily. And much cheaper probably and much more permanent in a construction zone than rumble strips or all these expensive signs. I mean, I think the signs are fine, in general, but they're not the only way we can communicate to people in vehicles. That's it. Yes.
Is the pattern of the magnets on the cart similar to what you would find in a vehicle, a commercial vehicle right now?
What do you mean? The patterns?
So the magnets, well, you have several magnetometers in the cart, right?
Correct. Those don't exist in a vehicle.
So
Yeah, yeah.
you have these attached.
Correct.
to this.
Correct. Correct.
Sir, these programmable materials, what about their reusability, like heating and reheating? Does they lose their performance?
Well, I mean, one can expect some permanent magnets degrade with time. So I think for temporary, I don't think it's going to be an issue. But yeah, one can expect some magnetic loss. So you need to have a signal that's high enough that even if it had some loss, you wouldn't be below the threshold.
Thank you for the presentation. Very interesting idea. Like I'm wondering why you don't use like a tape, magnetic tape that you can remove if you don't.
You could do that. There are some magnetic tapes. We use some of it. Yeah.
I mean, it would be more, like more cheap than this material. that you put inside.
Yeah, maybe. I mean, the only downside and there's nothing, I mean, if someone wanted me to do it tomorrow, that's what I would use. However, like we could imagine spraying a visible epoxy that has this in them, that's a little more permanent. It's more permanent than a tape that can easily be peeled up, particularly, let's say in the winter here. This is the issue with markings. They get covered up or the snow plow hits them and they get scraped up. So I'm not saying tape doesn't work. It just has some temporary problems. Yeah, Michael.
Yeah, great presentation, very interesting. And not to be that guy, but I'm always looking for like edge cases that might confound things. One, with buried utilities or possibly in motion charging, confuse this system. And the other is how would a car know the difference between, say, transverse lines or slanted versus the car approaches transverse lines obliquely?
Yeah, and we've actually looked at that case. I don't remember all the details, but we looked at that, the car would really have to be going at a really severe angle to actually make a difference. But in pavement charging systems would be a problem. Thankfully, there's none in the US that we would run over probably. If there's buried utilities, I mean, the nice thing about magnetometers is you have two of them, right? And if it's a utility that's buried, let's say 3 feet down, the top and this one, they see the same thing. And so it gets subtracted out. Now, if you have a piece of rebar laying on the ground, that would probably pick it up.
Thank you very much, Professor. Vehicle vibrations caused by road roughness and vehicle suspension system may affect the data collection. So my question is, besides fielding techniques, are there any other effective methods to identify and classify this noise signals for compensation in post-processing?
Yeah, I mean, those are good questions. Do you know a Pete? Or you work with him?
I work with Professor Kali.
Okay. Well, anyway, so this is our current challenge here, is what you're speaking of. I mean, there's a lot. So we've put some on the vehicle that Professor Talapur has over here, and vehicle vibrations, where some of the motors for the electric vehicle are relative to these magnetometers. They create a magnetic signal that causes some problems, particularly accelerating and decelerating. So these are all real issues that we've unfortunately spent a lot of time on this last semester trying to overcome some of these issues. So yeah, I mean, we've spent most of our time on signal processing in a real vehicle. So this is all nice stuff I've shown without any other disturbances. Even vibration of the sensors at some higher speeds will cause problems. So we have to be really careful how we fix them to the vehicle.
So I had a question about what you presented at first with the whole lane departure thing that Sachin did. So because putting that strip in the middle of the lane is going to require like milling and, you know, constructing it, can you, like Noor was suggesting, magnetize the edge, the marking, lane marking on either side? So instead of detecting that you're in the middle, now you're detecting how far you're off the edge of either edge. And that way, like, you can, I think, more easily implement this. Is that possible?
Yeah, I mean, I don't think you can put it at the edge because the magnetometer really looks either down right below the sensor, or if it's looking sideways, it has only a certain view. So if you're like 2 feet away, it's not going to get a great signal. Yeah, so it has to be underneath the car essentially, somehow. Yeah, Romez?
Yeah, thanks, Jeff. This is really interesting. When you said you shifted to work zones, I thought something totally different, because I thought it was still going to be lane keeping, because we have a project with Minnesota DOT where we looked at some of their pavement marking. We're looking at their pavement marking degradation, especially due to snow plowing and winter seasonal effects. And one thing that, you know, we notice is the markings, you know, in all these northern states generally are recessed, and the work zone, you know, temporary markings are not recessed.
Right.
So I thought that would be the perfect application for work zone, is, you know, because those work zone markings are going to go so fast because they're not recessed. So I was curious why the DOTs were so interested in speed. Is lane departure not the #1 problem in work zones anymore? Or, I mean, compared to on the normal highway?
You mean the speed?
Well, because you went after speed as the problem for the.
Speed and merging.
Right, speed and merging.
Right.
But what about lane departure and work zones? I mean, I would think that's a huge problem.
Well, that
especially
could be.
for us as a market.
Yeah, that could be too. In fact, P-Did showed me a vehicle running into barricades just now before this, Tesla's running into barricades that were just adjacent. So it kind of didn't see it at the camera system and just ran into it.
Yeah.
But there's nothing inherently, I like it better for lane departure, but sometimes people aren't listening, so you got to talk to some other people.
For the agency, for their employees and people working on the side, lane departure would be the most critical issue. So I was surprised that they were so kind of laser focused
Yeah.
on speed, it sounds like.
Well, I don't think anybody was laser focused on any of this. It was just my idea of pivoting away from, I kept talking to people about lane departure and no one seemed to be that interested in it. Minus the vehicle manufacturers were all really excited about it, but they don't own the roads.
We can take one more question.
I can go ahead. So I would like to ask you a clarification question regarding the enabling and disabling the magnet
Sure.
in the epoxy.
Okay.
How would this work? When you apply it, it's magnetized, but then you would have to heat it to demagnetize it.
Well, you mix the material with asphalt or concrete. You then have to heat it and have a magnet over it while you're heating it. You heat it to 120, apply the magnet, it cools below 120, and it has the permanent magnet feature. Okay, it stays there like that. But to demagnetize it, I just have to heat it without the magnet. Yeah, because then the atoms just move back to whatever orientation they want.
And is there any precaution to have in raining or snowing conditions with the epoxy? Does it affect the way it works?
No, I mean, it'd be like the same thing with the marking. You would apply it in dry weather, of course. But yeah, it shouldn't have, it's really a paint it's a paint epoxy that you would put for normal lane markings. But they're temporary. I mean, markings are temporary, so it would never be a permanent solution. But for work zones, it's temporary.
Thank you so much. And join me in thanking Professor Roesler one more time.
Thank you.